Hi, everyone. Apologies I can't be there in person, but I'm excited to share some of the work that my group and I have been doing recently. Um, hi, I'm Rose Cersonsky. I'm a new PI at UW-Madison in Madison, Wisconsin in chemical and biological engineering. And today I'm going to talk a bit about what one of my students, Arthur, has been working on, thinking about expanding density correlation machine learning formalisms for anisotropic particles and hierarchical systems. So often in our field of theory-driven studies of molecular interactions, we want to group one or more atom as a theoretical unit or particle. And so you can kind of think of this as a pragmatic choice where it doesn't make sense or you're not capable of resolving all of the energetics of a system at an atom level description. But I also like to think about this in terms of a logical argument. So it can either be out of necessity or pursuit of causal reasoning. So thinking about in a system where we only allow X to be true, where we eliminate certain degrees of freedom within our problem statement, what behavior can we explain? So both of these reasons can motivate us to want to think about more than one atom as a fundamental unit in our theoretical study. And so many people have thought about this so-called coarse-graining problem in machine learning from a standpoint of how we can optimize our degrees of freedom. There's some really beautiful work using variational autoencoders to essentially take high-dimensional simulation spaces and project them into low-dimensional latent spaces to actually do simulations. And then, of course, there's a lot of work out of Cecilia Clementi's group at FU Berlin thinking about using different sorts of architectures to map into these lower dimensional spaces. And these are very good for high performance aspects and generalizability, but typically these end-to-end models lack an intrinsic interpretability. So how can we understand what degrees of freedom we've eliminated or what we've lost by going into these coarse-grained spaces? And so this is kind of and often a paradigm of the two kinds of thinking about machine learning modeling, where the first says, okay, I've got a chemical system, and I want to take the rawest form of how I think about that chemical system and use an architecture to essentially build a relationship or a surrogate model or some sort of mathematical formalism to connect that raw input to some sort of target observable. And so this is what you would typically think of as our black box machine learning, where essentially we allow the algorithms and the computers to do a lot of the heavy lifting of the mathematics in between raw input format and target spaces. But on the other end, we have something we call bottom-up learning, where you take what we could consider raw chemical format and transform it into some sort of representation, some sort of numerical or textural format that is supposed to reflect our system at hand. And typically with these bottom-up approaches, we have a more gray box approach. We can use shallower networks and shallower architectures to be able to learn with similar, not always the same, but similar fidelity, our target properties. So what goes into this X here? And you'll hear a little bit, I'm going to guess more from my friend Andrea tomorrow about how we construct these sorts of features. But I like to think of it in terms of high school chemistry class or middle school chemistry class, using the American terms for our levels. We all have heard ways of representing chemistry in some sort of format. And the first one we always learn is a chemical formula. This is a text-based representation to encode the chemistry at hand. Now, for machine learning, this is not a great one because it's not unique. You can think of many different molecules that have similar or the same chemical formulas, but very different properties. And so this is why it's a lot more usual in text-based machine learning models to use something like a smile string, which also encodes the connectivity between different atoms as well as the aromaticity. Now, I often look at things where we worry about configurational space. And so these are also not perfect for those sorts of applications because it doesn't tell us the bond angles or the correlations between atoms or where things sit in space to each other. And different configurations of the same molecule will still have the same chemical formula or SMILE strings. And so that's where we might think about something like internal coordinates. So internal coordinates, or the XYZ coordinates and the species tags for our molecule, are the simplest, most raw form of what we would call a representation for these systems. And again, this is not perfect. Essentially, you have to have your machine learning model learn, oh, my system, if I was to move it over by an angstrom, is exactly the same. Or we have different sorts of orderings that might happen. And so this is where you get something maybe like an adjacency matrix that encodes the distances between atoms instead of just where they are. So what I'm kind of trying to get at here is that the quality of the features that you use to represent the chemistry that you're trying to study determine how easy a target is to learn and how much you actually learn in the process. And I like to use features such as numerical fingerprints, which are just basically numerical vectors that encode the configurational space of a molecule or a set of atoms. So in these representations, what do we want? Well, the whole idea with representations is that we have this nebulous structure space. We have this kind of unknowable, infinitely dimensional space in which all chemistry lives. And we're trying to project or trying to represent it in a smaller feature space that mimics the chemical similarity of our structure space, where we would expect if we change our chemistry smoothly, our features change smoothly. We would expect if we have two entirely different chemistries, they sit in entirely different spaces in our feature space. And we would also expect that if there's any sort of underlying symmetry to our molecule, such as an invariance to rotations, translation, permutations, that they all map to the same spot in our feature space. And we get added benefits if we also make our feature space, we get added benefits for additivity. So if we make a molecule as a sum of its parts. And there's many, many different frameworks that fit within this idea. Really, it's a lot of them are just terms of n-body correlations of atomic positions with different sets of bases. And so we had to think for a little while, okay, with all of these different ways of representing atomic environments, how would we want to represent a system based upon multiple atoms being our fundamental unit? Now, the best way that I think to do this is by working off of density expansion frameworks. So density expansion frameworks treat each atom as a density field, and then take the correlations of these density fields over different sets of bases in order to represent what we would consider the atomic environment. And what's nice about these density fields, this density field approach, is it's also been extended in many different directions, not in the least by my colleague Andrea, who will talk tomorrow. But for example, we can add in a spherical harmonic term in order to then map to a tensorial property of our configurations. We can also use message passing frameworks to extend these density expansions to also include information on iteratively larger networks. So let's go to the most common, in my opinion, of these density expansions, the smooth overlap of atomic positions, or the SOAP framework. With the SOAP framework, if I were to take my ethanol molecule here, what I would first do is I would represent each atom by a Gaussian density. Now, this I find very hard to look at, so I always flip back. But sitting on my carbon atom here, what I would do is I would look out into the neighborhood and take a histogram of what I see based upon a given set of radial bases and spherical harmonics. I would do this for every single atom in my system, where you can see that we have these different signatures for the different environments of these atoms. Now, whenever I do this in a more pedagogical context, I play the game of who can guess which atom is H1, H2, H3, and 4 through 6, because there's small little subtleties that show you the difference between these different atomic environments. Very clearly, H6 is the hydrogen sitting on the oxygen atom, because we see a much stronger set of peaks for our little radial explorer finding oxygen atoms. We see that H1 and H2 are sitting on our central carbon atom, and 3 through 5 are sitting on our terminal carbon atom. And so we can see right here, we have a very clear signature for the environments of our systems. And so we can take an average of all of these in order to represent our molecule for a machine learning purpose. Now, mathematically, this is what we're working with, where we've said that for a given N, L, and M, so these are the indexes of our radial bases and our spherical harmonics, we represent an atomic environment by looking at the density field expanded away from that environment, expanding over a given radial basis and a given spherical harmonic, where the three-body term that I'm showing here is just the product of two different density expansions across different radial bases. So to represent groups of atoms, we can leverage the flexibility of this. So we've got this equation again, where we've got our density expansion over radial bases and spherical harmonics. Now, SOAP will typically use a Gaussian density for point particles, or you might even see a delta function for underlying a lot of other machine learning representations. So what we just did is said, okay, well, what if we want to represent an ellipsoid? An ellipsoid is the simplest form of anisotropy we can induce to represent a group of atoms. Well, we can just replace this Gaussian density with a multivariate Gaussian that represents axes within our space. And what's nice about this is by smartly choosing our radial bases, we can compute these expansions efficiently and analytically to be able to represent our system. So what does this all mean? This means we now have a way to featureize configurations from a molecular rather than an atomic level. So say I have a nice little benzene dimer right here, where in the SOAP formalism, I would typically expand the correlations of every single atom center. Now I have what we call AniSOAP, or the anisotropic smooth overlap of particle positions. We can represent molecular configurations, including aspects of molecular geometry, mutual orientation, and molecular neighborhoods in a way that's compatible with machine learning and characterization. So now let's think about how this compares to our typical way of representing such systems. So I originally come from the classical mechanics fields, where we often are looking at liquid crystals just as the interactions of hard ellipsoidal bodies. And what we'll typically do is we'll do something like a prolate ellipsoid or an oblate ellipsoid to represent different sorts of molecular systems. And I will look at things such as in the smectic or the nematic phase, where smectic is orientationally ordered in layers and nematic is orientationally ordered without any translational order. Now, if you look at our PCA plots of the AniSOAP vectors for these different configurations, where the saturation of our color tells you how much orientational order, so how random are the orientations of the system. It's blue if it's a nematic phase and red if it's a smectic phase. We can see that the AniSOAP vectors really clearly delineate, first of all, smectic versus nematic phases, as well as our geometries. So these are the exact same PCA plot, but on the left, I've highlighted the points corresponding to the prolate ellipsoids, and on the right, I'm highlighting the points corresponding to the oblate ellipsoids. So again, American footballs versus flying saucers. And we can also see very clearly that the AniSOAP vectors can delineate strongly orientationally ordered phases in the smectic phase, as well as start to delineate those in the nematic phase. And if we look into further components, again, we can see that delineation between the different geometries, as well as these orientational orders with a much clearer delineation of the orientationally ordered nematic phases from the non-orientationally ordered nematic phases. So what we have is a smooth representation that simultaneously contains information on particle geometry, orientational ordering, and translational ordering, which is really important for being able to actually characterize these systems. The next question that we had to ask is, okay, can AniSOAP map to our traditional methods for ellipsoidal representations of molecules? So the traditional method for taking a molecular system and representing it as ellipsoidal bodies is called the Gay-Byrne potential. So the Gay-Byrne potential is a potential form that is based upon the rotation shape, where we represent our system in terms of these dilation matrices, as well as the distance between our ellipsoids, where we have a Lennard-Jones-like term, as well as different anisotropy corrections. So our goal here is to be able to show that if we were to learn a system based upon the Gay-Byrne potential, which is an imperfect representation, we can still be able to at least pick up that information. Now, a little nuts and bolts note is that when you calculate Gay-Byrne, you have to do an approximation based upon the distance of closest approach. So what is the closest distance between two ellipsoids, which is actually a really mathematically non-trivial problem. And so there's a lot of different approximations, the biggest one being the Perrin-Wortham equation for approximating this distance. And what we're really proud of with our representation here is that AniSOAP implicitly contains the information on the distance between two ellipsoidal bodies. And so we don't require an explicit calculation of this distance of closest approach. And so here is the plot that my student sent me at 5 p.m. last night of our learning of our unstable Gay-Byrne configuration. So we actually really wanted to challenge ourselves here and learn the most unstable version, because the stable version of Gay-Byrne is actually very trivial to learn. And so we can show that we have a 0.9999 R squared fit of learning these energetics using the AniSOAP representation. So this is where my student and I looked at each other and we said, okay, how far can we take this? And for the record, this is my student Arthur. He's a chemical engineering PhD. He's phenomenal. And we said, what is the most difficult system that would be most trivial to represent by ellipsoids? And that would be benzene, the smallest molecule that we figured we would well represent with an ellipsoid. So what we did is we took 7,000 benzene crystals generated via Pixel, where Pixel generates these symmetric systems, many of which are unstable. We then permuted a bunch of them to be able to ensure that we had some interesting symmetries in there. And then we use quantum espresso using PBE with the Grimm D3 dispersion correction to compute the energetics. And so we took all these configurations and represented them by their equivalent ellipsoidal geometry. So first, we want to measure the information loss going from the atomistic to molecular level representation. And to do this, we can actually leverage a method developed by my colleague Alice Gojinski, which is called the global feature reconstruction error. So say we have two representations of the same data set. So same exact data, but represented using feature vectors in X1 and X2. The global feature reconstruction error denotes the mutual information contained in those two feature sets, where if I say GFRE of X1 to X2 is 0, that means that my representation X1 can recreate 100% of the information contained in X2. But if it says 0.5, that means that X1 can recreate 50% of the information contained in X2. Now, one way you could think about this is temperature in Celsius versus Fahrenheit. So if you had a feature vector that was representing temperature in Celsius, you could fully recreate the temperature represented in Fahrenheit with a GFRE of 0. But say we had other information within our feature vectors, say humidity or say propensity for bad storms. These things might be correlated to the temperature, but we wouldn't be able to represent that with that set of features. So another way you can think about this, and this is what we showed in our paper earlier this year in Open Research Europe, is a way of understanding the importance of different hyperparameters. So say I had a set of water systems and I wanted to resolve different neighborhood shells in my water environment. I could use the GFRE to figure out when adding new features or adding new resolution of my features would not provide me any new information. So you can see here, in order to reserve the first HH shell, we need 10 radial basis functions, but the third one we need 32. And so this tells us essentially when we've saturated the information in our representation. So the way that we can use this in our systems is by looking at how much we lose by going to this molecular level view. So here I've got a plot where on my x-axis I'm showing the radius of my ellipsoid along the xy plane, and then on my y-axis I'm showing the radius along the z-plane. So you can think of above this line we're looking at prolate ellipsoids. Below this line, we're looking at oblate ellipsoids. And along the middle, we are looking at spheres. So we're testing out different geometries of the ellipsoidal representation for our benzene systems. And we compute the GFRE for going from the atom level representation to the molecular level representation at these different points. And what we can see here is actually a mathematical proof that, in a very flexible terms, that a benzene ring is an oblate ellipsoid, where we see the lowest GFRE when we look at about our radii being about, our semi-axes being about 3 angstrom. And we see a lot of information lost by using isotropic representations or a sphere representation for each of the benzene molecules. So then we can actually do supervised tasks. So for reference, if I was to train a smooth overlap of atomic positions supervised model on these energetics, this would be my accuracy, where I can get about an R squared of 0.98 and a root mean squared error of about 9.2 millielectron volts per atom. If I take each of my molecules and put a SOAP representation on their molecular center, so an isotropic density field on each molecule, our accuracy absolutely nosedives, where we can see that we really can't learn the energetics of our benzene systems by using isotropic representations. If I use AniSOAP, we see that our plot essentially flattens back out, where we can get a much higher accuracy by using the AniSOAP representation for our molecular centers. And just a little note that Arthur wanted me to make sure to say is this is done solely with cross-validated regularized ridge regression. So we're able here to learn the energetics of unstable benzene systems using a molecular level representation and linear regression. And because of this, we're actually able to understand why we fail in certain cases. So what we can essentially say is if we learn our energy using our AniSOAP vectors and some sort of linear regression weights, we can also add in a correction term based upon that atom level description. So if I was to learn the error in our regression using our original SOAP vectors, we get our parity plot to flatten out once again. So what this is saying is we can provide atom level corrections to the molecular level descriptor in a way that retains this compatibility. And because I now have this regression, I can leverage we can leverage principal covariance regression to understand the places where AniSOAP fails. So PICO-VAR is essentially a mapping technique that is using the interpolation between PCA and linear regression to provide a sort of interpretable structure property map to look at how different sorts of chemical features correlate with properties of interest. And so we build a PICO-VAR map on the atom level description and the error in the AniSOAP regression. So what you're seeing here is you're seeing a map where we have a correlation with the error in learning the energetics from a molecular level description. And the map also shows the correlation between chemical diversity, where we can see that AniSOAP most often fails in places where our benzene configurations are rotationally degenerate. So that means that we would have the same AniSOAP representation for different atomic level systems, or for very, very unstable configurations with strong atom-atom interactions. Now, why did I just show you the place where our methodology fails most often? Because it proves the principles that we're trying to put forward. These are the places where it should fail. A molecular level description will never be able to really resolve these atom level degeneracies or these very strong atom-atom interactions. So to summarize, what we've shown is that expanding density-based machine learning representations provides a way to characterize systems at a molecular level and enables interpretable machine learning. This is going to be a forthcoming paper out of our group, as well as I'll put up the references for all of the other things that I've mentioned. And then I've been making a really active note in my talks in the last year to highlight this point that if current trends don't change, fields such as chemical engineering and material science will not reach gender parity in our lifetimes or in the next couple of centuries. And so a couple of us got together and wrote up a paper called Not Yet Defect Free, the current landscape for women in computational materials research, that underlines why this is, what we can do, and what the effects of this are that really need to be fixed in order to ensure that we're able to provide a inclusive and diverse community for people to thrive within. And so with that, I will thank our funding sources and be happy to take any questions.
Thank you. Thank you for a very interesting presentation. I'm sure there are some questions here in the audience. Can you hear me, by the way?
Yes, I can.
Yeah, good.
Does this work? Okay. Hi, thanks for the very fascinating talk. I think the idea with the anisotropic Gaussians was really, really interesting. I was wondering about the applications of these methods because your, I suppose, coarse-grained is like a fair description of your simulations, your coarse-grained simulations. These are already, I would assume, relatively fast because I'm from a more quantum chemistry background. These are, for me, these are classical or classically coarse-grained simulations. Is the purpose here for the machine learning potential, I will call it machine learning potential, to speed these up with respect to the already classical simulation? Is the purpose more to, or is the purpose to get a more accurate result?
Yeah, so I think that one thing that we're doing here is we're able to essentially cast to these problems into the frameworks of the more efficient simulation methods. So one really difficult problem in applying things like the Gay-Burn potential or what I would consider more top-down coarse-grained potentials to different systems is the fitting problem. What do we consider a good fit? How do we consider it actually retaining the fidelity of the problem? And so, yes, the accuracy piece is really important, as well as, the speed up piece is very important. But here we're trying to kind of aim for how can we merge these scales and say, what is the best way to represent benzenes within the Gay-Burn potential? How might we be able to augment that potential very simply by adding back in one atom level description? So kind of bringing these scales together in terms of information fitting in and hierarchical things. So one thing that my student is thinking about right now is how might we apply this to certain sorts of polymeric systems where it's not necessarily possible to always represent every single atom, but we can actually show from the bottom up, from a data-driven standpoint, what is the best way to throw it into these more empirical type potentials.
Okay, yeah. I'm going to be looking forward to that. That sounds extremely interesting. Thank you very much.
I'm looking out in the audience here to see if there are some more questions. So if not, in respect of time, I think we should continue with the next speaker and thank Rose again for a nice presentation.
Thank you all. Take care.